Hello everyone, I am Rishisha and I am a graduate student at the University of Buffalo. Today we will be looking at the Lagrangian modeling of a four-bar using Maple. We select a four-bar mechanism because it is a standard example used in most robotics courses for understanding how a constraint mechanism works. We select Maple because it has very good symbolic computation capabilities. To start with, we'll define our problem. We have a standard four-bar mechanism with an inclined first link and relative angles theta1, theta2 and theta4. We omit theta3 because it is not going to be required in our calculations. Start with, we are first going to look at an overview of the entire process. We will be defining the variables in Maple and their differentials, giving their positions of the different centers of masses, which are positioned for this case at the centers of the links, and then we'll be finding out the velocities by differentiating these positions. The next step would be to find the kinetic and potential energies of the entire system, and hence the Lagrangian. The next step would be to find a variable space, that is to just define a variable space with theta1, theta2 and theta4 as being the primary variables in the analysis, and then defining the number of degrees of freedom, etc. The next step would be to actually calculate these matrices, namely the constraint matrix, the mass matrix and the force vector. The last step would be to print these matrices, check them and then export them to different files as needed. So to start the process, we'll restart the Maple kernel. We'll be using the alias command for defining variables as function of time. So the standard thing to do is alias theta1 is theta1 of t, theta2 and theta4. Similarly, we'll have theta1 dot, theta2 dot and theta4 dot by differentiating these variables with respect to time. The next step would be to find the positions of these different centers of masses. They are given here, x1 being the position of the first center of mass, the second and the third. The next step would be to find out the position of the breakaway point in the mechanism in terms of two sets of variables and equate them. The first set would be theta1 and theta2 and the second set would be theta0 and theta4. So we name those two representations of the same point as x2a and x3a. So by equating x2a and x3a in a further analysis, we will be creating the position constraints in the system. The next step is pretty straightforward. We just differentiate the velocities of the different centers of masses, label them as x1d, x2d and x3d. The next step would be to calculate the vector norm of this and combine them with respect to trigonometric identities, so that we have all these sorts of combinations of angles which are easier to look at and understand. So we have x1s, x2s and x3s as being the magnitudes of the velocities of the three centers of masses. The next step is to actually multiply these magnitudes with the different masses to find out the kinetic energies and multiply the rotational magnitudes of the different centers of masses with their inertias so as to find out the rotational kinetic energies. So we do that using m1 by 2 into x1s, similarly for m2 and m3, and the whole procedure for the rotational kinetic energy. When we add that, we have an expression. Similarly, we find the potential energy of the system by finding the potential energies of the three masses and adding them up. The Lagrangian is just a difference of these two. The next step is to define a variable space. The variable space in our case is just going to be theta1, theta2 and theta4. And we define the differentials of these variables with respect to time and also the double differentials of these variables with respect to time. The next step would be to now find the number of variables in the system. In this case it is 3 and it is easy to see, but this is done in order to sort of generalize the process which follows from here on. We have n-var as being the dimension of var, which is 3. We have the number of degrees of freedom in the system. We know that it is 1. And so we calculate the number of constraints, which is going to be 2. The next step is to actually calculate the Euler-Lagrange equations. Now at this point, we can use the Euler-Lagrange command in variational calculus package of Maple, but we would like to develop our own procedure in order to understand how the Euler-Lagrange formulation works. So we see that the Euler-Lagrange formulation is nothing but dou by dou t of dou by dou q dot of L minus dou by dou q of L is equal to 0. There are other tau terms in this, which we will be covering in a later session. We simplify this process, that is, we break this process into 2 or 3 different parts. We first of all substitute for the differential of the variable and the variable itself with temporary variables temp d and temp. The next step is to find out the differential of the given Lagrangian with respect to the temp d, which is the differential, and then differentiate that with respect to time after substituting the original variable and its differential. We do this because Maple does not allow us to differentiate with respect to variables which have been declared as functions of time. And as you can see, the last step is just a similar thing to the first step, which differentiates with respect to q and then returns the whole answer. Let's run this procedure. To check the validity of this procedure, we now take the first variable theta1 and use the Euler-Lagrange command of Maple and get a result. The next step is to do an Euler-Lagrange using the formulation that we have just devised and then add the two. So we add equation 6.2 and equation 6.3 and get a 0. This implies that both of them are just different in sign but otherwise accurate. The next step would be to run this for the entire set of variables. So we define the equations as a matrix of n var by 1 and compute it for I from 1 to n where we have the Euler command. After running this, we can see that we have 3 different sets of equations and we can extract out now the force matrices and the mass matrices from this.